The early 19th century was a time of great scientific ferment. Isaac Newton's ideas about the nature of light, dominant for over a century, faced a formidable challenge. Enter Thomas Young, a brilliant English polymath whose curiosity led him to question the established order. Young, a physician by training, possessed an unquenchable thirst for knowledge, delving into fields as diverse as linguistics and physics. It was in the realm of optics that he made his most profound mark, forever altering our understanding of light and the universe itself. Young's most celebrated contribution to science was deceptively simple. Thomas Young, an English polymath, was fascinated by the nature of light and its properties. His curiosity led him to devise an experiment that would challenge the prevailing theories of his time. He devised an experiment, now known as the double-slit experiment, that would expose the wave nature of light with startling clarity. This experiment was groundbreaking because it provided a new way to understand light, which had been a subject of debate among scientists for centuries. Imagine a beam of light like that from a flashlight directed towards a barrier with two narrow slits. This setup might seem simple, but it holds profound implications for our understanding of the physical world. Behind the barrier lies a screen. This screen is crucial because it captures the light that passes through the slits, allowing us to observe the resulting pattern. What pattern would you expect to see on the screen after the light passes through the slits? This question is at the heart of Young's experiment. Intuitively, one might expect two bright bands on the screen, corresponding to the light passing directly through each slit. This expectation aligns with the idea that light travels in straight lines, much like particles. However, Young observed something far more intriguing. His keen observations and meticulous experiments revealed a surprising result. Instead of two distinct bands, he saw a pattern of alternating bright and dark fringes, an interference pattern. This pattern suggested that light waves were overlapping and interacting with each other. This unexpected result provided compelling evidence that light, contrary to Newton's corpuscular theory, behaved as a wave. The interference pattern indicated that light waves could combine to produce regions of constructive and destructive interference, much like ripples on a pond. Young's experiment was a pivotal moment in the history of science. It challenged the dominant particle theory of light, which had been championed by Isaac Newton. Newton's theory suggested that light was composed of tiny particles or corpuscles that traveled in straight lines. Young's meticulous notes and sketches from his experiments provided a detailed account of his observations. These records were crucial in convincing the scientific community of the validity of his findings. Today, the double-slit experiment is considered one of the most beautiful and elegant experiments in physics. It is often used to introduce students to the wave-particle duality of light, a fundamental concept in quantum mechanics. Modern versions of the double-slit experiment use lasers and advanced equipment, but the underlying principles remain the same. The experiment continues to inspire and educate, demonstrating the wave nature of light in a clear and compelling way. Thomas Young's legacy in physics is profound. His double-slit experiment not only advanced our understanding of light, but also paved the way for future discoveries in the field of quantum mechanics. His work reminds us of the power of curiosity and the importance of questioning established theories. As Young once said, the pursuit of knowledge is more valuable than its possession. His double-slit experiment exemplifies this philosophy, showing that even simple experiments can lead to groundbreaking discoveries. To grasp the significance of Young's discovery, imagine dropping two pebbles into a still pond. The ripples created by each pebble spread outwards, eventually overlapping. Where the crests of the ripples coincide, they reinforce each other, creating a larger wave. Where a crest meets a trough, they cancel each other out, resulting in still water. This phenomenon, known as wave interference, explained the pattern observed in Young's experiment. The light waves passing through the two slits were interfering with each other, creating regions of constructive interference, bright fringes, and destructive interference, dark fringes, on the screen. Young's experiment provided crucial support for the wave theory of light, challenging the prevailing corpuscular theory and paving the way for a deeper understanding of the nature of light and electromagnetic radiation. Section 4, A Quantum Revolution, Planck, Einstein, and the Dawn of a New Era. As the 19th century gave way to the 20th, the world of physics was on the cusp of a revolution. The established norms and principles that had governed scientific thought for centuries were about to be upended by a series of groundbreaking discoveries. The classical understanding of the universe, governed by the deterministic laws of Newton and Maxwell, was about to be shaken to its core. These laws had provided a framework that explained the motion of planets, the behavior of light, and the forces of electricity and magnetism with remarkable precision. The seeds of this revolution were sown by the work of physicists like Max Planck and Albert Einstein, who introduced radical new concepts that would forever change our understanding of the very fabric of reality. Their work was not just a minor adjustment to existing theories but a complete overhaul that required a new way of thinking about the universe. Planck, while studying black-body radiation, stumbled upon the idea that energy was not continuous, but rather came in discrete packets, or quanta. This was a radical departure from the classical view, which held that energy could be divided into infinitely small amounts. Einstein, building upon Planck's work, proposed that light itself was quantized, consisting of tiny bundles of energy called photons. This idea was revolutionary because it suggested that light, which had always been thought of as a wave, also had particle-like properties. These groundbreaking ideas laid the foundation for the development of quantum mechanics, a revolutionary new theory that would challenge our most fundamental assumptions about the nature of the universe. Quantum mechanics introduced concepts that were not only counterintuitive, but also deeply unsettling, such as the idea that particles could exist in multiple states at once, and that their behavior could be influenced by observation. The early 20th century was a period of intense debate and experimentation. Scientists from around the world gathered at conferences to discuss these new ideas, often engaging in heated debates about their implications. The old guard of classical physics was reluctant to accept these radical changes, but the mounting experimental evidence was impossible to ignore. One of the most famous experiments that demonstrated the strange nature of quantum mechanics was the double-slit experiment. This experiment showed that particles such as electrons could behave as both waves and particles, depending on how they were observed. This duality was a cornerstone of the new quantum theory and challenged the very nature of reality. Another mind-bending concept introduced by quantum mechanics was the idea of superposition, famously illustrated by Schrödinger's cat thought experiment. In this scenario, a cat in a sealed box could be considered both alive and dead until the box was opened and the cat's state was observed. This paradox highlighted the strange and counterintuitive nature of quantum mechanics. Today, the legacy of Planck and Einstein's groundbreaking work continues to influence modern science and technology. Quantum mechanics has paved the way for innovations such as quantum computing, which promises to revolutionize fields ranging from cryptography to materials science. The journey that began with the radical ideas of Planck and Einstein has led us to a new era of scientific discovery and technological advancement. The dawn of the quantum era has not only deepened our understanding of the universe, but also opened up new possibilities for exploration and innovation. From the tiniest particles to the vastness of space, the principles of quantum mechanics continue to shape our quest for knowledge and our pursuit of technological progress. The revolution that began over a century ago shows no signs of slowing down, as we continue to unravel the mysteries of the cosmos and harness the power of the quantum world. Section 5, Electrons at the Double-Slit, unveiling the wave-particle duality. The double-slit experiment, initially designed to probe the nature of light, took on a whole new dimension in the quantum era. This experiment, which dates back to the early 19th century, was originally conducted by Thomas Young to demonstrate the wave nature of light. By shining light through two closely spaced slits, Young observed an interference pattern on a screen behind the slits, a hallmark of wave behavior. In the early 20th century, physicists began to explore the quantum world, a realm where the rules of classical physics seemed to break down. This new frontier was filled with mysteries and paradoxes that challenged our understanding of reality. The advent of quantum mechanics brought with it a new way of thinking about the fundamental nature of the universe. A pivotal moment came when the double-slit experiment was repeated not with light, but with electrons, the fundamental particles that constitute electric current. This experiment was conducted by physicists such as Davison and Germer, and later by others, who sought to understand the behavior of particles at the quantum level. When electrons were fired at the double slits, the results were nothing short of astonishing. Astonishingly, the electrons, despite being particles with mass and charge, exhibited the same interference pattern as light waves. This meant that electrons, which we typically think of as discrete particles, were also displaying wave-like properties. The interference pattern suggested that each electron was somehow passing through both slits simultaneously and interfering with itself, a concept that defied classical logic. This startling discovery revealed the wave-particle duality of matter, a cornerstone principle of quantum mechanics. The idea that particles could exhibit both wave-like and particle-like properties depending on the experimental conditions was revolutionary. It suggested that the nature of reality at the quantum level was far more complex and nuanced than previously thought. Electrons, and indeed all quantum entities, could behave as both waves and particles depending on the experimental setup. This duality is not limited to electrons but extends to all fundamental particles, including photons, protons, and even larger molecules in certain conditions. The wave-particle duality has profound implications for our understanding of the universe, influencing fields ranging from quantum computing to the fundamental nature of reality itself.